So let's use our newfound knowledge of logarithms to help us solve some exponential equations. The first thing to keep in mind is that logarithms aren't always the answer. Often it could be way simpler to do other methods such as finding the same base. Let's take a look at these first few questions here. If I'm asked to find 4 to the x plus 5 equals 64x, to find x in that equation, how could I do that? Well, if we remember, it's much easier to deal with these types of equations if they had the same base. And unfortunately, they don't have the same base right now. We have a base of 4 on the left-hand side, right, and a 64 on the right-hand side. Is there anything we can do to the 64 to make it have the same base as 4? Well, 4 to the power of what gives us 64? And the answer is 3. 4 to the power of 3 gives us 64. So we can actually write this. We'll leave the right side as it is because it's already in that lower base. 64 to the power of 3. We can write that as 4 to the power of 3, right? So all I've done here is I've written 64 as 4 to the power of 3. Now we can simplify that right-hand side a little bit. X plus 5 equals, when we have an exponent to an exponent, like 3 to the power of x here, inside the bracket and outside the bracket, remember we can just multiply those exponents. That's one of our exponent rules. So this is going to equal 3x. So because now our bases are the same, in order to make this equation true, we know the exponents must be the same. They must be equal to each other in order for this equation to be true. So we would write, therefore, x plus 5 is equal to 3x, right? Because those equations, or the exponents, have to be equal. And then we can just solve this equation. So we bring that x to the other side, 2x equals 5. So x has to equal 5 over 2. And that's the solution to that equation. See, we didn't have to use any logs there. Nothing fancy. This is just making the bases the same. We can do the same thing for the next two questions. So I actually want you to pause the video here, try those two questions yourself, and when you're ready, you can unpause and see the solutions. So here we go for those other two questions. In part B, the same base, in order to get the same base on the left and the right hand side, we had to do 2 to the power, right? So 4 is 2 to the power of 2, 8 is 2 to the power of 3, and then we expanded those exponents in by multiplying them, and then set the exponents equal to each other and solved, -9. For C, the common base that they all have is 3, right? 81 is 3 to the power of 4, 9 is 3 to the power of 2, and 3 is already in the base 3, but remember root 3 is just exponent of 1/2. So then we just distribute these exponents. For this question, we distribute, or this term we distribute the exponents, and same thing. Now the one thing to remember for this line right here is that when we multiply things with the same base, we add the exponents together, correct? So 2x plus 6 plus 1/2, and that's what I did in this next line, which simplifies to 2x plus 18 over 2 as the exponent. So then we can equate the exponents, and then we can solve, and x equals 3/2 in this case. So notice in these first three questions, we didn't have to use any logarithms or anything like that. We just had to find the same base. So whenever we can do that for a question, it's usually the easier route to use. Now, sometimes we can't do this. For example, this next question. I'm going to zoom in down here. Example 2. 4 to the 2x minus 1 equals 3 to the x plus 2. Is there any common base between 4 and 3? Well, none that's going to be a whole number at least, right? So there's no way to do this using that previous technique. So instead, just as the instruction says above, we can actually make use of logarithms here. And the key is to take the log of both sides. So whenever we get stuck, we're not able to find the same base, take the log of both sides. So let's do that. So we're going to take the log of 4 to the 2x minus 1. So this is all inside the log, equals log of 3 to the power of x plus 2. Notice how I didn't put a base for the log, because it's assumed we're going to take the log with base 10, which is what your calculator can do, right? You can technically do any base as long as you do the same base on both sides. So we've taken the log of both sides, the log base 10 of both sides, and now we can apply some of our logarithm rules to simplify this. How are we going to do that? Well, remember, one of the really useful rules is that we can move the exponent down in front of the log, right? And we can do that on both sides. So on the left side, what that's going to look like is in front of the log, we're going to end up with a 2x minus 1 log, and then the only thing left inside the log is 4. And on the right-hand side, we're going to do the same thing. We're going to move down that x plus 2 log of 3. Okay, that looks a little bit simpler. We got rid of all the exponents, which is the beauty of logs. We can get rid of exponents really easily. So now let's try to simplify this thing. We can distribute now this log. So remember, log 3 and log 4 are just numbers. We can get those numbers by just plugging them into our calculator, essentially. So there's a few ways to go about doing this, and I'm going to just start by dividing both sides by log 4. So I'm going to divide both sides by log 4. Divide by log 4. That's going to cancel out over here. So what we have on the right-hand side, well, what we have on the left-hand side is pretty easy. It's 2x minus 1. And then what we have on the right-hand side is x plus 2. And then we can do times log 3 over log 4. And log 3 over log 4, we can just literally do that in our calculator. Log 3 divided by log 4. And what you get when you do this is 0.7925. Plus a whole bunch of other decimals. I'm going to take 4 decimal places, and that's usually what I do. I take 4 decimal places until the end, and then we round at the end. So now this is just a linear equation. We can solve this linear equation, right? 2x minus 1 equals, distribute that 0.7925 in, so 0.7925x plus 2 times that, right? Which is going to give us 1.5850, right? So a little bit messy. We have a bunch of decimals here, but that's okay. So we'll bring that 0.7925 to the left side. So we're going to do 2 minus 0.7925, which is going to give us 1.2075x equals, and I'll move that 1 to the other side. So we're going to end up with 2.5850. And then divide, obviously, both sides. And you end up getting x equals 2.1407. I'm just going to round to 2 decimal places. 2.14, and I'm going to put the approximate symbol there because this is an approximate answer. So what we just found is we just found the solution to this, the value of x that can make this equation equal this equation, right? Previously, maybe a way that we could have done this is just with a little bit of trial and error, plug in a bunch of stuff for x until we find the right answer. But now we found algebraically, just using logs, the exact answer. Now, a further question for you is, what does this mean graphically? We should recall that essentially what solving equation is, it's finding the value of x that works for both of these, right? But another way, graphically what it means is, where does this graph, this function, intersect with this function? What x value does that occur at? So what I'm going to do is I'm going to throw these two equations into Desmos, and we can see what that looks like. So there, I've plugged both equations into Desmos. Note how I had to put the brackets around the exponents, or else Desmos thinks I want to move out of the exponent. So that's a little trick. Just put what's in the exponent in brackets so that Desmos knows what you're trying to do. So looking at the graph, it's hard to see if those two things intersect yet, right? So we predicted, actually, based on our answer, that they should predict at 2.14. And it looks like 2.14 is all the way up. It's sort of off the graph, right? So we're going to need to go up, 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 up. Ooh, look how steep these things are. That's one of our things about exponential functions, right? They get very, very steep very fast. They grow very fast. So looking here, all the way up here at around the value of a y value of 95, we have what seems to be a point of intersection. And if I click on that point of intersection, look what it tells us. The x value is 2.141. So those two exponential graphs did actually cross at that value. So again, this is an easy way to check your solutions. Throw it into Desmos, and you can see whether or not you're getting the right answer. So here are some general tips when solving these types of equations. What we have below is just a bunch of assorted logarithm and exponential questions that we're going to solve, but keep these tips in mind. So first of all, solve by writing in log or exponential forms when possible. This means just if you can rearrange something that looks like a log into an exponential form, you can actually just solve it some of the time. It's not too hard. Or if you can just rewrite something in log form, it makes it pretty easy. Secondly, you can try combining and simplifying logs. So put logs together or take logs apart using some of your laws of logs, like the product or quotient rule, and that can really help us out. And lastly, if we're going to end up taking the log of both sides, which is sort of usually our last resort, if we can't do any other algebra to do it, make sure to isolate the log values first. Get them by themselves, and then or the exponential terms by themselves, and then take the logs of both sides. Simplify them as much as possible before you take the logs, essentially. Okay, so let's try some of the questions from example 3. Always with these questions, I would recommend try them first, pause the video before I get to the solution, and then unpause to see if you're right or not. So starting off with example 3a. So to do this one, let's think, can we give them the same base? Is there anything 5 to the power of something gives us 30? Nope, there's no same base here. Can we simplify this in any way? No, not really. So our next idea is to use a log, right? And remember, our definition of a log is that it's going to be log to the base is the bottom thing. So log base 5, and the thing that goes beside that base 5 is what's on the other side, the 30. The exponent is the thing that goes on the other side of the equation, 2x plus 3. So this is actually a problem from the previous lesson, right? We're just able to rewrite that equation as a logarithm. Now, in your calculator, you can either do log base 5 of 30 if your calculator is able to do that, or, because that's not one of our common bases, we can just use change of base to evaluate the left-hand side. So change of base, remember, is just going to be log 30 over log 5, and that's going to equal 2x plus 3. We can do that log 30 over log 5 in our calculator, very easy, divided by log 5, and that's going to give us 2.1133 equals 2x plus 3, and then we can just solve that equation by rearranging. So we're going to do that minus 3, and then we're going to divide by 2. So we end up getting x is equal to approximately 0.44, negative 0.44. Okay? Moving on to the next question. Again, I highly recommend you try these questions yourself before watching me do the solution. So this is a case, again, there's no sort of common base between these three things, right? 4, 7, and 8. That looks complicated. Obviously, there's no common base. So what should we do? Well, we can't really write it in logarithmic form either because we have this silly 4 out in front, right? So let's get rid of that 4. Let's divide both sides by 4. What do we get when we do that? We're going to divide this by 4 to make that go away. We get 7 to the x minus 2 is equal to 8 over 4, which is just 2. There we go. Now we have something that's just a straight up exponential equation, exponential on the left side and a constant on the right side. So we can do the same thing we did for the previous question, right? We can just write this as a log, not too difficult. So it's going to be log with a base of 7 of 2 is equal to x minus 2. And again, using our change of base formula here, log base 2 over log, sorry, not base 2, log of 2 over log of 7 is going to give us x minus 2. And we can easily solve that. Log 2 divided by log 7 is 0.3562 equals x minus 2. And then just solve that by adding 2. And then we're going to get actually let me write it out as x equals approximately 2.36. There we go. So this next question, we can write this in exponential form, right? We can just rearrange the log in exponential form because we know what this means. 4 to the power of 2 is going to give us x plus 3, right? That's using our circular rule. 4 to the power of 2 gives us x plus 3. 4 to the power of 2 equals x plus 3. There we go. That's pretty straightforward. 16 equals x plus 3. So x must equal 13. That was super easy, right? Next one looks a little bit more complicated. And again, try it yourself. And then unpause the video when you're ready to go. So here, this is a case where, see how the bases of all the logs are the same? We can evaluate that log base 5 of 10 on the right side if we really wanted to, but because they all have the same base, can't we just combine these all into one log? That might be able to help us in this situation, right? And there's actually a few ways to go about doing this. For example, we can one way that we can do it is we can just combine these two logs on the right. Remember what one of our law of logs was, or our logarithm rules, was that when you have two logs being added with the same base, we can combine what's inside the log, right? We can basically just multiply those things. So this is like saying log base 5 of x minus 3 times x, right? We're multiplying the things inside the logs equals log base 5 of 10. So we can simplify, obviously, what's in that equation on the left as log base 5 of x squared minus 3x. We know that's going to equal log base 5 of 10. And similarly to how we can equate the exponents, we know the exponents have to be the same for an exponential equation. We know in order for this equation to be true, the thing in the left here and the thing on the right have to be equal because the log bases are the same, right? Log base 5 and log base 10. Or sorry, log base 5. So this must equal this for this equation to be true. So we can do that same thing we did in the last question, or the last type of question, right? Where we can actually just equate the things inside the logs. And of course we can rearrange this, x squared minus 3x minus 10 equals 0. And we have a nice little quadratic to solve here, right? So we can obviously try factoring this first, and it factors quite easily as x minus 5, x plus 2 equals 0. Therefore, our x values are going to be 5 and negative 2. So I've got a question for you. Are both of these answers correct and true and make this statement true? So we can check by plugging in the values of 5 and 2 into the left side and into the right side to check, but I'm actually going to do it by throwing both sides into Desmos. So hang on, I'm gonna put it in Desmos, and we'll talk about it there. So I plugged both these equations into Desmos, and one thing you should know actually before plugging them into Desmos, in order to find the log, you can just type log basically, but you won't get the base of whatever you want. You'll get a base 10 log. In order to change the base of the log, hit the functions button, go to miscellaneous misc, and click the log with the little a. See, it's the middle one in the second last row. So click that, and then that allows you to input the base that you want into the log. Okay, but anyways, going to the graphs. So, and another thing, sorry, another quick point about using Desmos with this. When you graph a constant, like log base of 5 of 10 just evaluates to a number, right? And the number is 1.43. You have to put y equals, or else it won't know that you want to graph that constant. Anyways, look at the graph. Where do they intersect? They clearly intersect at 5. But where is this intersection of negative 2? Does it happen? And the answer is no, it clearly doesn't happen. Why is that? Well, remember, logs have a condition. Whatever is inside the log has to be greater than 0, right? We can't take the log of a negative number because nothing, if we raise to an exponent, is going to give us a negative number. Nothing with a positive base, at least, is going to give us a negative number. So this log has an asymptote at 3, and the reason why it's at 3 is because that's what would make this log value 0. So this value of negative 2, if we were to plug this into the equation here, right, we'd have negative 2 minus 3, which is negative 5. So it's like taking log base 5 of negative 5. 5 to the power of what is going to give us negative 5? Well, nothing. It's impossible. There's no solution to that problem. So because that's the case, we say that this is extraneous. It's not a solution to the problem, right? Our solution is that x equals 5. And if we want to do this a little bit more methodically, what we could say we could actually tell right off the bat, there's a condition to this logarithm, right? That x minus 3 has to be greater than 0. So basically what that tells us is that if we rearrange that equation, we're basically going to get x has to be greater than 3 in order for that to be true. There's also a condition from this one, right, that x would need to be greater than 0. But this one trumps that. So this basically tells us x is greater than 3. So the easiest way to do this is get your solutions and then plug each solution back into your logs and see if it's going to make any of them negative. So it's a little bit of a check. And so in this case, our only solution is that x equals 5. X is 2 is extraneous, so it is not a solution. We actually should have done this for the previous question too, but I didn't check that. We should actually check that 13 works, but 13 obviously makes that log positive, so we're okay. So moving on to question E, we can't really do anything about this right off the bat because we have this 2 in front of this log here. That's making it a little bit more complicated, right? It's like there's a log base 2 on this side, the log base 2 on this side, but that 2 is sort of messing us up. What could we do with that 2? Well, remember, one of our rules of logs is that if there's an exponent inside the log, we can bring it down in front. So we can do the opposite too. If there's a number in front of our log, we can actually bring it up to the exponent. So I could rewrite this as log base 2 of x is equal to log base 2 of 5 squared, right? And then I can simplify that. Log base 2 of x is equal to log base 2 of 5 squared is just 25, clearly, right? So by inspection, it basically says the things, because the bases are the same, the thing inside this log and the thing inside this log, because these things have to be equal, those things inside have to be equal. So we could say, therefore, x must equal 25. All right? Okay, moving on to the next one. Uh-oh, this one's a little bit crazy. We have an x as our base. So the unknown is actually the base of the exponential, which is sort of interesting. First step maybe is to make this look like something a little bit more friendly to us. Let's turn this into exponential form. So it's going to be x to the power of negative 2 is going to give us 0.04. So we can just write that out. X to the power of 2 is equal to 0.04. That doesn't look so bad. That's an equation we know how to solve, right? Oh, sorry, next to the negative 2, my bad. X to the negative 2 equals 0.04. So the question is, how do I do this? Well, the first thing I like to do is get rid of that negative on the exponent, right? And I could just do that by raising both sides to the power of -1, right? So that's going to give me x squared equals 0.4 to the -1. And that's just like doing 1 over 0.04, right? Which is going to give me, if you just do that, you can do that in your calculator, it's just equal to 25. Okay, cool. So now let's solve this equation. How do we solve it? Obviously, we just take the square root of both sides. It's going to get rid of that. So x equals 5. Is that it? Well, when we take the square root of something to find an answer, we know that there's actually 2 roots. There's 2 things that could have given us 25, right? Plus or minus 5. But now we have to go back to our log and see if this actually makes sense, if both of those answers make sense. Does positive 5 work as our base in this original equation? Yeah, clearly, right? That's not an issue. 5 to the power of -2 gives us 0.04, correct? Now, we might think -5 to the power of -2 also gives us 0.04, which it does. But the problem is, logs are only defined when the thing inside the log is greater than 0, but also when the base is greater than 0. The base can't be negative because log isn't defined. It isn't defined when the base is negative. So the base, the b in general, and we know this, we took this note in a previous note, base has to be greater than 0. We end up getting all sorts of wacky undefined functions if the base is not 0. So because the base needs to be greater than 0, x cannot equal -5. Clearly, it has to be greater than 0. So our only solution is that x equals 5. That is our only correct solution. So moving on with our examples, we're almost done here, a few more examples. We have log to the 5x, log of 5x, 5 to the x equals 7. So this looks a little bit different. What's our base? Remember, our base is just going to be 10. So let's start out by writing this in exponential form. That can usually help us. So it's going to be 10 to the power of 7 is going to equal 5 to the power of x, right? That's something that we can do. Now, this isn't obvious where we can go from here, right? How can we basically do this? We can do 10 to the power of 7 is going to give us something. It's going to give us basically, what is it, 10 million, I think, equals 5 to the x. That gets a little bit complicated. Instead, so this is one route, and you could take this route, but I'm actually going to go a different route. I'm going to look at this, and I'm going to say, oh, look, we have an exponent inside the log. Can't I just move that down in front? And I can. I could do x log 5 equals 7. Isn't that easier to solve? Because I can just do x is equal to 7 over log 5. Right? That's it. I've solved the equation. All I need to do is plug that into my calculator. It's already in base 10, so it's not like we need to do any change of base or anything like that. And the answer comes out to x is approximately equal to 10.01. So there are other ways to find this solution, like I was getting at up here, but I think that's the quickest way. So sometimes it's quicker to actually move the exponents down in front, or sometimes, like in a previous question, right, it's sometimes easier to move what's in front up into the exponent. Really, you just have to do a lot of these questions to see the different strategies and which ones are going to work. This is another case where it looks like we got a lot of different things going on. We got lots of 4s, and we got a 20 to the x and a 180. A lot of things going on. So let's simplify. And the first thing we can do to simplify is obviously get rid of that 4 in front. Let's just get rid of that 4 in front by dividing both sides by 4. So we're left with log base 4 of 20 to the x equals 180 divided by 4, which comes out to 45. Right? Now, how can we further simplify? Similar to the previous question, that x inside the log is sort of confusing things, because if it wasn't there, we could, like, log base 4 of 20 is just a number, right? 4 to the power of something is going to give us 20. So bringing that x to the outside is going to make things simpler for us, right? Because then I could just do x is equal to 45 over log base 4 of 20. Now you can use your change of base or your calculator, whichever method works for you, in order to solve that log base 4 of 20. But if you do it, the final answer should come out to 20.82. And just by quick inspection, we actually should have done this for the previous question too. Is this going to work if we plug it into our question? Is it going to make anything inside the log negative? And the answer is no, right? 20.82 is not going to make anything inside the log negative, so we're okay. That is our answer. I want you to pause the video now. Try these last 3 questions yourself. When you unpause, I'm going to show you the solutions for all 3 of them at the same time, so make sure you've actually tried them all before you unpause. So here we are. Here are the solutions. Let's go through them quickly one at a time. So for our first question, I combined what's on the left side. So I combined the 2 logs that were on the left side using our product rule, right, or product law of logs. That gives us this. And then we realize the base was a, so we actually didn't know what the base was. But it doesn't matter what the base is, because it's on both sides, and what's inside the logs have to be equal to each other, right? We know the bases are going to be equal, so all that matters is what's inside the logs, and we can equate those, simplify, and solve. At the end, we get x equals -5 and 2, and if you check those with our original logs, when x equals -5, the logs are going to be undefined, right? This will be negative, this will be negative, this will also be, well, this one will be positive, but the other ones will be negative. So basically it can't be an answer. 2, however, works for all 3. That's going to be positive here, it's going to be positive here, it's going to be positive here. So our only solution is that x equals 2. For this one, for B, this is sort of an interesting question. You got a log inside a log. But if you really understand how logs work, it shouldn't be that bad. Using our circular rule, we know that the outside log, 5 to the power of 1 is going to equal log 25 base 25 of x, right? And that's all I did here. 5 to the power of 1 is equal to log base 25 of x. So that's okay. So 5 to the power of 1 is just 5. And then we have another log, so we can use this our circular rule again, right? 25 to the power of 5 is going to give us x, right? So 25 to the power of 5 is just 9,765,625. So that is our answer there. The last question is a little bit more algebra intensive, and it's a system of two equations that we have to be able to solve. I actually started off with the second equation. I started off over here. And what I did is I simplified this equation. I actually turned it into the exponential form. So x minus y is our base. So x minus y to the power of -3 gives us 8, right? And then what I did is I simplified it by moving the negative exponent to the other side. So it became 1 over 8, right? And getting rid of that negative exponent there. And then taking the cube root of both sides to get rid of the cubed on this side. When we do that, x minus y equals 1/2. And then we can just solve for x. X is equal to 1/2 plus y. Once we have that, we can start working with our second equation, or our first equation, I guess. The first thing I did is actually turn it into logarithmic form, because it frees up this x plus y. A little bit difficult if the x plus y is in the exponent, so the log's going to free it up to be on this side, right? Then I plug this in to my equation. So instead of x plus y, it's 1/2 plus y plus y. So just 1/2 plus 2y when I plugged that into the equation. So that's what I did here. I substituted this in for that x. Once I've done that, I can just use a change of base to evaluate what's on the left here. Log of 16 over log of 1/2. And that just turns out to be -4, exactly -4. And that's because we can actually, we can raise 1/2 to the power of something to get 16. But anyways, that becomes -4, so then it just becomes an equation we can solve. Our y ends up being -9 over 4, and then if we substitute that back into this equation, we find out that our x has to be -7 over 4.